Okay, a very good morning to each and every one of you. I hope you can hear me clearly and can see the screen also clearly.
Good morning, sir.
Very good morning. Thank you. Okay, so yesterday we finished off with power distribution and how we parallel generators, etc. Okay, not only that, we also did shaft earthing and all those things. Those are minor topics, but then even certain questions that are asked, okay, those can be carrying 3-4 marks on that, especially earthing of your shaft, okay, of your main engine shaft. If you don't earth your main engine shaft, you can have a current which is going to be flowing down the shaft caused by electrostatic buildup of electricity, okay, and that electrostatic buildup is because of your ICCP current, okay, and that your shaft is insulated due to that lubricating oil that is over there. So once the shaft sits down, or even after a certain amount of time where there is sufficient buildup of electrostatic energy, that can still arc across, okay, and then cause arcing and damage your main engine bearings, okay. So we saw that and we completed that topic yesterday. And finally, now we are coming to the last topic of the number of topics that I will be undertaking, okay, and that is transformers. Once we complete this transformer topic, we start the cycle all over again with sensors. So if we complete transformers today, then we will start again with sensors. Okay, so what is a transformer? The definition of a transformer is it is a static device. There are no moving parts in it. That is why it is called static. Why did we have a static generator? Because nothing excepting the rotor was moving. Okay. Whereas in your brushless generator, you had your rotating diodes, you had your rotating exciter field, you had your main rotor field. Okay. All those were rotating. Whereas here, in your static generator, only the rotor field was rotating. Everything else was stationary or static. Likewise, in your transformer, there are no moving parts. Everything is stationary, and that is why it is called a static device. Okay, where energy from one circuit is transferred to another by means of electromagnetic induction, and most pertinent to note is without changing of frequency. So if you have 60 hertz at your primary, voltage is induced into your secondary at the same frequency. There is no change in frequency. Okay, and since we are talking about electromagnetic induction, everybody knows electromagnetic induction is governed by Faraday's laws. Okay, so Faraday's laws of electromagnetic induction will be used as far as your transformer action is concerned. Okay, even in your motors, it is a transformer action. How is it a transformer action in your motor? You have your primary. Which is your primary? Your stator coils are your primary. Which is the secondary? Your rotor. Your rotor is the secondary. Okay, where we had those steel bars that are shorted out on either ends. As I said, it looks like a firki. Okay, so that is acting as the secondary. Okay, so Basically, that is also a transformer, excepting there you're having a rotating magnetic field. Here there is just a changing magnetic field. It is not rotating and therefore will be inducing a voltage into the stationary secondary. Okay. Right. What are the common uses of a transformer? We generally use it as a step up or step down. Remember, we said if you're going to use DC, it's going to be very hard to do that. What do we do if you are using DC? Then you have to use a chopper circuit, as we had in your particular Mega. Okay. Whereas if you're having AC and you're having transformers, you can very easily step up the voltage. You can very easily step down the voltage. Number two, used as a means of isolating a direct connection between power source and loads. Okay, isolation transformers. We electrical officers are quite used to this isolation transformer. How? Suppose your washing machine is having an earthing problem and you just cannot, remove that earthing problem because it's gone right deep into the electronics of that particular circuit. Okay, unless you change that electronic circuit, it's not going to go away. Okay, so if you ask the company, the cost of that electronic circuit is like buying a new washing machine. So they will say, try and do your best. They're not going to give you a new washing machine. So what do? You do your best. You buy an isolation transformer where the number of turns in the primary is equal to the number of turns in your secondary. So if you're getting 220 volts over here, you will also get 220 volts on your secondary. So this is connected to the source and this one is connected to the load. That is a washing machine. Okay, and by doing this, you are isolating that earthing that is occurring on your washing machine. You are isolating it from the source. Otherwise, what was happening? Your 220 volts, okay, was directly connected to the load. So this earthing is going to directly reflect on your source and you would be getting that earthing problem. Okay, so you're going to isolate by this type of a transformer where primary and secondary windings will be having the same number of turns. From number one above, it is also used for your auto transformer motor starter. We've already seen the auto transformer motor starter where we had used it, okay, for your listening, okay, all those emergency equipment such as your main air compressor number 2, steering gear compressor, steering gear motor number 2, your emergency fire pump. All those are going to have that auto transformer. Just a very quick recap. Okay, this is your one winding. This is your auto transformer. Okay, and because we are using a step down transformer, you are having your primary and then you are taking tappings. What were those tappings? 50%, 65%, and 80%, right? Of the applied voltage. So the applied voltage is over here. And as I said, generally we are having the tapping on the 65%. So you're reducing that by about 20, 25, 30%. 35% thereabouts. Okay. And only 65. So if you're going to have 100 volts in your primary, then only 65 volts you're going to be giving to your secondary. And by reducing the voltage over there, you are reducing the starting current. And that's how you are safely starting those motors. Okay. Right. So that was what we had discussed when we did the motor starter, the auto transformer motor starter. And basically your auto transformer has only one winding from which you're going to take tappings. The tappings will be either a step up or step down type. Okay. Now, if you remember when we did the power generation, etc., that topic, okay, we said that the generators are rated in kVA. Okay, apparent power. It's not true power. Why? And at that time also, I had mentioned that the transformers are also rated in kVA. Okay, again, apparent power. The simple reason is because those manufacturers of those generators, the manufacturers of the transformers, they do not know what the loads are going to be connected to the transformer or to the generator. If they knew what the loads were, then they will be able to calibrate their particular equipment to give you in kW. kW is real power. But real power can never be there is because on board the ship, you can have a lot of inductive loads where the current lags the voltage. They are in the form of all your motors, your heater coils. So mostly on board the ship, our particular load is a inductive load. And therefore, your generators, if they're going to give real power, it has to be actually a resistive load. And therefore, if you remember, the power factor can never be 1. Okay, because if cos theta is equal to, if the angle theta is equal to 0, cos theta is equal to 1. That, as we know, is an impossible thing. Okay, because of the inductive loads that we have on board a ship. Okay, so since the manufacturer does not know to what load this transformer or that particular generator is going to be connected to, whether it is inductive, whether it is resistive, or whether it is a capacitive load, therefore, they are going to be rating it in kVA. Okay? Right, so let's get down to the transformer itself. A transformer has certain parts, one of which is the core. Okay, what is the core? The core has limbs, yokes, on which your particular windings are wound. Okay, why are we having a core? We can have just a winding. Okay, let's put this winding over here. And we can put the secondary winding. So this is your primary, this is your secondary. And as long as we are going to give a AC source to this, okay, you will have an electromagnetic changing lines of force over here that is going to cut your secondary and you will get a voltage output over here. Okay, you'll get a voltage out. The lines of force are cutting this secondary, but not all the lines of force. Okay, therefore, in order to make it as efficient as possible, if you've seen the symbol of a core, the symbol of a core is by these two parallel lines. What is this core doing? It is generally made up of ferromagnetic material. When you say ferromagnetic material, it means whatever the lines of force over here, they are going to be also induced into this core, which is going to strengthen these lines of force, electromagnetic lines of force. Remember, the secondary is not kept like this. It is wound on this ferromagnetic material. So when the electromagnetic lines are going to be concentrated by this ferromagnetic material, that means maximum lines of force created by your primary will intercept your secondary, and therefore you're going to get as much as voltage as possible. You're going to be reducing your losses, okay, if this core was not there. Okay, and we'll come later on also, by having this core, we are going to have a certain loss. So basically, there is a sort of a compensation. The losses would be more if the core was not there. Okay, right. So let's see what this core is made of. The core, as we said, is made of ferromagnetic material and are of two types: the hollow type and the shell type. Okay, what is the hollow type? Let's magnify this a little bit more. Okay, so you can have a block like this, okay, a block like this, you can have a solid block. Okay, but why we are not going to be using a solid block? Okay, with a thing hollowed out over here, and then you can put your primary on this and your secondary on this. Okay, why we're not having a solid block, we'll see. But instead of that solid block, you're going to have this solid block cut into very thin strips or plates, you can say, with a hollowed out section. Each of these plates are going to be insulated, and we will see why they are going to be insulated from one another. But, okay, coming back to this one, we are going to have these type of various laminated thing, as it's called a laminated core. It is going to be cut into thin sections, and each section is going to be insulated from each other. When they are going to be put together, it will look like a solid block like this, but in reality, it is not. It is this, several of these thin sections are put together and makes it look like a thing. And on one side, okay, on one side, you are winding the primary. On the other side, that is this side, you are winding your secondary, and your output is taken. Okay. So this is the hollow type for the simple reason there is a hollow in between. Okay. And this particular type is having several sections that are put together, but each section is having laminations or insulation. It is dipped in varnish such that you are not going to be having a conducting current that is going to be flowing. Remember, this is a ferromagnetic material. So any electromagnetic lines of force that are created by your primary, that is also going to induce a voltage in this ferromagnetic. So that means there's going to be a current. We will see that as part of a loss called iron core losses, okay, or I squared R losses. And you also have eddy current losses, which we will be taking up a little later. Okay, so this is the hollow type of core. What about the shell type? Again, you're going to have several of those slices. Okay, so a block is sliced up, as you can see here. But it is sliced up in such a way that you have I sections, okay, and E sections. The I section is called a yoke. The E section is called a limb. So several I's and several E's make up this particular thing called the shell type. Now you could add your primary wound on this side and the secondary wound on that side. But that is not going to help matters. So where are they going to wind the primary and secondary? They're going to wind it on your central limb of the E. Okay. First is the primary. And of course, you're going to have to insulate your primary windings, on top of which your secondary windings, which are also insulated, are going to be wound. And your output is from one side, your input is from the other side. So your hollow type just consists of particular square shape or oblong shape, whatever it is, okay, all sliced up, insulated from each other and put together to look like this, like this. Okay, when it's going to be compressed, it's going to look like a solid block. Okay, and the shell type is having E and I section. The I section called the yoke, E section called the limb, and you're going to be winding it on the central part of the E. Okay, both the windings, primary winding, secondary winding, you can have a step up, you can have a step down, but both the windings are insulated from one another. Okay, so what is the relationship between the number of turns and the voltage? Remember, we spoke about step up and step down. So if the number of turns in your primary is greater, primary turns are greater than your secondary, then it becomes a step down. Okay, step down transformer. If your primary windings are less than that of your secondary, in other words, your secondary windings are greater than that of your primary, it becomes a step-up transformer. Okay, and the relationship of the turns and voltages are this. Generally, in your writtens, you will be given some problems to solve. Okay, so you'll have to memorize this formula. V1 by V2 is equal to N1 by N2, where V1 is the primary voltage, V2 is the secondary voltage, N1 is the number of turns in your primary, N2 is the number of turns in your secondary. Okay. What is the relationship between current and the number of turns? As you can see, they are inversely proportional. So if you're going to have a step down, that means voltage is lower, your current will have to be higher. And if your voltage is a step up, then your current will be step down. Okay, just the opposite. So your thing as far as your formula is concerned, I2 by I1 is equal to N1 by N2. So here's a complete comparison between all of them. Okay, so they can give you some parameters and ask you to calculate what would be the voltage or what would be the current output for a given number of turns of your primary and secondary. Okay. Okay, so there is a question. What would happen if the primary is supplied voltage and the secondary winding is left open? It's a very commonsensical answer to that question. Okay, let's say we were using that same isolation transformer. Okay, so this was your primary, you have supplied 220 volts or 110 volts. Okay, secondary had the same number of turns, so you are getting again 220 volts. Okay, this is plugged in to your source. Okay, you're having it plugged in. Okay, and you forgot to take the plug out and the switch is on for that. Okay, meanwhile, what have you done? You've disconnected your washing machine. Okay, and you kept these two terminals open. Okay, if you're doing that, voltage is induced into your secondary, and if you are going to touch these two terminals, you're going to get a God Almighty big jolt, a shock. Okay, it can even electrocute you. Okay, if the current is going to be high enough, normally even 10 milliamps is enough to kill you. 10 to 15 milliamps is enough to kill you. Okay, so if you're going to touch these two terminals, you're going to get a shock. Another thing that can happen, that is one very dangerous thing that can happen. Okay, another thing that can happen is when this was connected to the washing machine, there would have been a current flowing, okay, through the washing machine, through the secondary windings in that manner. When a current is going to be flowing through the secondary, remember, every current carrying conductor has its own electromagnetic field. It is because of this primary having a current flowing from the source through the primary that you are having these electromagnetic lines of force. Likewise, here also, when it was connected to the washing machine, okay, you had those electromagnetic lines of force mainly because of the current flowing through your secondary. Now, when you have current flowing through a conductor, its own electromagnetic lines of force are going to cut the primary again. When it's going to cut the primary, it is going to induce a voltage into the primary because of the current flowing in your secondary. Voltage induced into your primary because of that, because of the secondary, is called as back EMF, as you must have heard. Okay? Or back voltage. What does this back EMF do? Or what does this back voltage do? Because it is reintroduced into your primary, it is going to cause a current to flow, a current that is going to oppose the original current. And by opposing the original current, it is limiting the current flow through this and keeping it to a safe value, therefore protecting your primary from getting burnt out. Okay? This is when it is connected to the washing machine. But now that you've isolated your washing machine, yet you kept your primary plugged into the source switch is on, voltage is induced into your secondary, but now since you have disconnected your washing machine, there is no current flowing in your secondary. Because no current is flowing in the secondary, there is no back EMF put into your primary. Since there's no back EMF induced into your primary, there is no current caused by this back EMF. And therefore, there is no opposition to the current that is now going to be flowing through the primary, which can be very high. When it's going to be very high, obviously your insulation is going to get heated up. That instrument, whatever the thing is there, the transformer, the primary is going to get heated up. And very soon your transformer will become kaput. Your primary will get burnt out. Okay? So, a changing AC voltage causes a small current to flow, creating a magnetic field. This magnetic field induces a voltage into the secondary. If the terminals are left unprotected, somebody accidentally touches those connections, they will get an electrical shock. So this is number one. Number two, impedance of the primary is low, and if current is allowed to flow continuously with the secondary open, secondary induces a counter voltage, as we said. This was the back EMF. Okay? Induces a counter voltage into the primary that keeps the primary current in check, because a voltage is induced in that a current that is caused by this back EMF is going to oppose the original current flow. Okay? So, induces a counter voltage in the primary, keeping the primary current in check when connected to the load. Then this current, okay, if it is disconnected from your secondary, this current is now not going to be there, and your primary current, your normal primary current, if your load is disconnected, will now shoot up and cause your primary winding to get burnt out. Okay? Everybody clear? Okay, what about instrumental panels? Excuse me. Instrument transformers. Okay, just give me a moment. My throat is gone. Okay, so your instruments on your main switchboard, your emergency switchboard, we have ammeters, we have voltmeters. Okay, so how are those particular things? Suppose one of those meters has got damaged. Okay, if we keep the secondary open over there, remember we are sort of stepping down, they are not step up. They are potential transformers, they are current transformers. Okay, and once again, if you remove that particular ammeter, voltmeter from that particular panel and leave the secondary open, you can receive a shock. Okay, you will receive a shock. If you're going to keep it shorted, remember, even if you keep it open, it's not going to reflect very much on your primary over there, in the sense your primary is not going to be burnt out, because you're using the primary as part of your bus. Okay, so that's not going to get burnt out very easily. You'll need thousands of amperes for that to happen. Okay, so it's not going to affect the primary in that case. Only the secondary, if it is kept open, you will be exposing somebody to a shock. Mainly what one does is either short it or put a proper value resistance in that particular thing and keep it that way till you replace it with a new meter. Best, they say, is shorted because, as I said, it's not going to reflect onto the primary being your bus bars, because they are not going to get damaged. When you get the new instrument, then connect it accordingly and you're back in business. Okay. Okay, so we spoke about those transformers that are then supplying those particular instruments, and therefore they are called instrument transformers. Okay, they are voltage transformers and they are current transformers. Voltage transformers are generally stepped down. Okay, so you're going to have your potential transformer in this manner. Okay, so it's taken from your bus bar. Sometimes directly it is wound from your bus bar and you're having it as a step down over here to your voltmeter. Your current meter can also go directly, and you have a winding. You would have seen, if you open the MSB, you would have seen that thing, and then it is taken directly to your ammeter. Okay. So your voltage transformers are always used as a step down, as you can see, where a higher supply voltage is stepped down to 110 volts, 220 volts. Okay, if you are having 440 volts to 440 volts, then it does not need to be stepped down. It can be just like an isolation transformer, where 440 is just taken from here and directly connected, very much like a current transformer, excepting that it is graduated or calibrated to give you a volt reading. Okay, so it's taken exactly like a current transformer and giving you a voltage reading. So 440 volts to 440 volts. Current transformer always uses a step-up ratio for voltage, as current is inversely proportional to the voltage. Okay, so you can have voltage, but you can graduate or calibrate this meter to give you the voltage reading. Okay. Coming to the losses. Now your transformer is about 90% efficient. Okay, where is that 10% gone? It could have been 100% efficient. In other words, whatever energy that is there in your primary is transferred 100% to your secondary. You're not losing out on anything. Okay, so where is this 10%, or sometimes they say have efficiencies up to 98%. So where is that 2% gone? Okay, you have something called as transformer losses, and your transformer losses are, number one, copper losses. What are copper losses? Remember, your primary, your secondary, they are made of copper. Okay, any conductor has its own resistance. A conductor like silver. Okay, so suppose this is silver. Let's take a particular color for that silver. Okay, so this looks more like silver, right? Silver will have, say, 10 ohms. For example, this is out of the hat figure. Your copper, say your copper looks something like this, will have, say, 20 ohms for the same length. Okay, and say aluminium, okay, aluminium for that same length, okay, will have, say, 30 ohms. All are conductors. Each conductor, depending on what the conductor is, will have its own internal resistance, and that resistance is called resistivity. Why? Is because, for example, silver will be having more free electrons than copper, and copper will be having more free electrons than your aluminium. Okay, it is these free electrons that are flowing around that are going to carry this current. So if you're going to have more free electrons, then this resistance for this particular conductor, which is silver in this case, is going to be much less. It is having less free electrons as far as copper is concerned as compared to your silver. Therefore, the current that is going to be carried by this is going to be much less than that of your silver. Okay, because of that. Likewise, your aluminium. Okay, but generally on board ship, aluminium is not used. Certainly, silver is not used because it becomes very expensive. Therefore, we are using copper. So how does one reduce this particular thing? Okay, we can reduce it. Okay, now I'm going to show you the cross-sectional area. Sorry, this is still in that. Okay, a cross-sectional area. If the copper winding of your transformer is going to be this much, and your copper winding of your particular transformer is going to be this much, obviously there's going to be more resistance to the current flow over here as compared to over here. Okay, so it depends on your cross-sectional area. If your cross-sectional area is more, your resistivity is decreasing. Okay, resistivity is rho directly proportional to the length divided by area. And area here is cross-sectional area. So if cross-sectional area is going to increase, your resistivity decreases. Okay, and also depending on the length, if the length is very long, obviously your resistivity is going to increase. Okay, so these, because you're using copper, these are called as copper losses. So current is going to be flowing through this. Okay, higher the current that is going to be there, your loss is going to be even more. And they are also called as I squared R losses. Your copper losses or I squared R losses are one and the same thing. Okay, so this is one of those losses which will add up and reduce the efficiency of your transformer. Okay. Everybody understood up till here what are copper losses, etc. Now your second loss is called the eddy current loss, also called as iron core losses. Okay, now coming back to these two things over here, your hollow type and your shell type of cores. I said whether it is hollow or whether it is the shell type, the core is cut into very thin sections. And then each section is insulated from one another by means of varnish. Okay. So what are these eddy current losses or iron core losses? As I mentioned that when your primary is wound on one of those limbs, the core is made of ferromagnetic material. So a changing magnetic field caused by your current flowing through your primary due to the AC, that is going to induce a voltage into that particular core, that soft iron core, ferromagnetic core. Okay? When voltage is induced into something, a current is going to flow. Exactly as I said, when you're going to leave your secondary open, the current is not going to be flowing in the secondary, so no back EMF induced into your primary. So here, your core is a soft iron magnetic core, which when your primary is supplied with a changing electromagnetic field, that same electromagnetic field that is changing and causing voltage to be induced into your secondary, that same thing is going to induce a voltage in this soft iron core. So when a voltage is going to be induced over there, a current is going to flow. What is this current called? This current is called eddy currents. When you're going to have eddy currents flowing, they will oppose Okay, excuse me. Not only the electromagnetic lines are forced into your secondary, but they will cause the core to get heated up. Remember, whenever you're using a transformer, just touch the core of the transformer. That is normally the external part over there. On the internal side, it is all insulated from one another. Okay, the outside gets really heated up. You touch the transformer, it is quite heated. Okay, so heat is doing nothing. It's only a waste of energy, and that is called as a loss. And because the eddy currents are causing this heat and an unnecessary loss, this is also called as eddy current loss. Okay, so how do we reduce these losses? That is why instead of having a solid core, that core is cut into very thin slices, and each slice is taken and dipped in varnish and then put together to form the soft iron core. You are isolating each of these slices from the other by means of varnish or other insulating materials, generally varnish, and it is then put together to form the soft iron core. It will have the same property of a normal ferromagnetic material, okay, excepting that although voltage is induced into those slices, because of the insulation material between those slices, those eddy currents are going to find it very hard to flow. So your eddy currents are reduced drastically. So also your heat is reduced drastically, and your eddy current loss is reduced quite a bit. So eddy current loss, also called as iron core loss or iron loss. Okay, everybody clear with this? Okay, before we go on to the third loss, that is hysteresis loss, let us see how your particular transformer works. Then we will discuss hysteresis loss, and then we can see a video on the hysteresis loss.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at how transformers work. Now this follows on from our series on electrical engineering, so do check out the other videos if you've not done so already. Links are in the video description below. Coming up, we'll be looking at how to create a magnetic field with electricity, why only an alternating current can be used in transformers, how a basic transformer works, then we'll look at step up and step down transformers, and finally we'll finish on three-phase transformers. Now there are two types of electricity, AC and DC, but transformers can only work using AC or alternating current. Now if you don't know the difference between these two, then please first of all watch the video on electricity basics first. Again, you can find links to these videos and other useful videos in the video description below. When we connect an AC generator to a closed loop of cable, a current will be able to flow through this cable, and the direction of the current will alternate backwards and forwards with the rotation of the generator. The alternation means that the current reaches its maximum and minimum point during the cycle, which gives it its sine wave pattern when connected to an oscilloscope. Now you can think of this as the tide of the sea as it changes direction and reaches its maximum and minimum point. As the current flows through the cable, it will emit a magnetic field. If we pass DC current through the cable, the magnetic field will remain constant. But if we pass AC current through the cable, then the magnetic field will increase and decrease in strength and changes polarity as the current changes direction. If we place multiple cables together and pass current through them, then the magnetic fields will combine to create a stronger magnetic field. If we then wrap the cable into a coil, the magnetic field will become even stronger. If we then place a second coil in close proximity to the first coil and then we pass AC alternating current through the first coil, then the magnetic field it creates will induce a current into the second coil, and this magnetic force will push and pull on the free electrons, forcing them to move. The key component here is that the magnetic field is changing polarity as well as intensity. This change in intensity and direction of the magnetic field constantly disturbs the free electrons in the secondary coil, and this forces them to move. This movement is known as electromotive force, or EMF. Electromotive force does not occur when we pass DC current through the primary coil, and that's because the magnetic field is constant, so the electrons are not being forced to move. The only time it will cause EMF is very briefly when the primary circuit is opened and closed, or when the voltage is increased or decreased, and that's because these actions result in a change to the magnetic field. Therefore, we use alternating current as this change occurs constantly. Now, the problem with this setup is that a lot of the magnetic field from the primary side is being wasted because it's not in range of the secondary coil. So, to fix this, engineers place a core of ferromagnetic material such as iron in a loop between the primary and secondary coils. Now, this loop guides the magnetic field along a path to the secondary coil so that they will share the magnetic field, and this makes the transformer much more efficient. Now, the use of an iron core is not a perfect solution. Some energy will be lost through something known as eddy currents, where the current swirls around the core and this heats up the transformer. And this means that the energy is lost as heat. To reduce this, engineers use laminated sheets of iron to form the core, and this greatly reduces the eddy currents. Transformers are manufactured to be step-up or step-down transformers, and these are used to increase or decrease the voltage simply by using a different number of turns within the coil on the secondary side. In a step-up transformer, the voltage is increased in the secondary coil, and this will mean that the current will decrease. But don't worry too much right now about why that occurs. We'll look at this in a later electrical engineering video. To increase the voltage in a step-up transformer, we just need to add more turns to the coil on the secondary side than the primary side. In a step-down transformer, the voltage is decreased in the secondary coil, which means that the current increases. To do this, we just use less turns in the coil on the secondary side compared to the primary side. For example, a power station needs to transport the electricity it has generated over to a city some distance away. The power station will use a step-up transformer to increase the voltage and reduce the current, as this will reduce the losses through the long transmission cables. Then, once it reaches the city, this will need to be reduced to make it safe and usable by buildings and homes, so there will need to be a step-down transformer. The transformers for commercial buildings and power stations are usually in a three-phase configuration. You'll see these placed around your cities and towns, and they'll look something like this. These three-phase transformers can be made from either three separate transformers that are wired together, or they can be built into one large unit with a shared iron core. In this setup, the coils will typically sit concentrically within one another, with the higher voltage coil on the outside and the lower voltage coil sitting on the inside. Now, these coils are insulated from one another so that only the magnetic field will pass between the two coils. To connect the two sides, there are many different configurations, but one of the most commonly used is to connect the coils in a configuration known as delta Y, sometimes referred to as delta star. This refers to the primary side being wired in a delta configuration and the secondary side being wired in a Y configuration. The center point of the Y side, where all three connectors meet, is often grounded, which allows for a neutral line to also be connected. We'll cover transformer connections and calculations in other more advanced videos, as this can get quite complex. So for now, simply focus on how they work to build your base knowledge. Okay, that's it for this video. Thank you very much for watching. I hope you've enjoyed this and it has helped you. If so, then please don't forget to like, subscribe and share this video. You can also follow us on Facebook, Instagram, Twitter and Google+, as well as our website, theengineeringmindset.com.
Okay, so that was putting everything in perspective in that video. We saw the losses, but they did not mention what was this hysteresis loss. They also didn't mention what was copper losses. Okay, so we have already seen what are copper losses. We've seen in that previous video the eddy current losses. And now we've also seen how we can reduce those losses. But let's come to this thing called hysteresis loss. Okay, and when we see the video, we'll be able to understand it better. Okay, so we are still talking about that magnetizing core, that soft iron core on which your primary and secondary are wound, such that you have maximum lines of force from your primary concentrated and cutting your secondary, making your transformer as efficient as possible. But what happens in this case? We said that the soft iron core is a ferromagnetic material. That means in that particular core, sorry, let me change the color. In that particular core, whether it is, sorry, it's not coming. Whether it is the hollow type or the shell type, let's take the hollow type. Okay. Okay. You will have in this ferromagnetic material, that is why it's called a ferromagnetic material. You will be having a lot of tiny magnets. Okay, lot of tiny magnets all spread around in this particular thing. They will be maybe north this way, south here, south this way, north this way, south this way, north this way, you know, just scattered around. Okay. Now, when you have your primary wound on that, that is also an electromagnetic lines of force, which you saw earlier. You are having north and south, those electromagnetic lines of force. And one time it is north-south, then it becomes south-north, as you saw, changing electromagnetic lines of force. Okay, so one time you are going to have north on the top, south at the bottom, and then next time you're going to have south at the top and north at the bottom. Okay, so when your primary is wound, say on this type of iron core, it is going to try, when it is in this north-south direction, and organize all these particular tiny magnets, such that if this, just taking as the big one as north and south, and these ones are all in different thing, they will make it such that this is south and north. Okay, all these over here. Okay, and then when it changes sign, then it is going to become north and south. All these are going to be rearranged. So for these magnets, these tiny magnets to be arranged in such a way that all the north are pointing one way and all the south are pointing one way, it is going to follow this particular curve. So here on your x-axis is the magnetizing current caused by your AC cycle. Okay, let's make this a little bit more clearer. Okay, this is your AC cycle, right? So as you're going positive, let's say you're going to have this north-south for your main electromagnetic field. And all these tiny magnets will start getting organized, all with north in one way, south the other way. It's getting magnetized, getting arranged. And then finally, at this particular point, all these tiny magnets will be arranged with such a way that you'll have all north one way, okay, and all south in the pointing in the other direction. All these tiny magnets will get arranged properly. At this particular point, we say that saturation has been achieved. Any further current, any further voltage or that, this thing is not going to think. So therefore, you're going to have this saturated. Okay, so saturated. Let me make that more straight. So you have reached the saturating point, and no matter how much you try to increase a magnetizing current, Okay, that is this one. You're not going to change anything further because they have already got arranged. Okay. Now that was happening whilst your particular AC cycle, the current, the magnetizing current has reached its maximum. You have reached saturation point. Now your AC cycle is coming downwards towards zero. Okay. When it is coming downwards towards zero, again, these things start to get hera-fairy, if you want to do. They start getting back into its original position. So it is going to follow this particular curve. But when the magnetizing current is reduced to zero, that is at this point, we find that all these magnets are not gone into the hera-fairy position. There are still some magnets which are still having that north and south pointing in the direction when it had got magnetized away. Therefore, at this particular point, we see that all the magnets are not become hera-fairy as it was when it first started off. Okay? What one has to do? Now one has to take the current, the magnetizing current in the opposite direction. And therefore, let's say around here. Yeah, Mr. Nitin Mishra, I've told you all guys to mute your microphones, please. Thank you. Okay, don't unmute your micro. Maybe it is accidentally, but please keep a watch on your microphone. Otherwise, you disturb my trend of thought and you're disturbing the other students also. Okay. Right. Okay. So at this particular point, although the magnetizing current has come to zero, you are still having some magnets in this core still arranged in this manner with north in one way and south in the other way. Most of the others are gone into the hera-fairy position, all scattered. Okay. So to make it into the original thing of completely scattered, okay, or completely demagnetized, exactly like when you're magnetizing a screwdriver. What happens when you magnetize a screwdriver? All those tiny, tiny magnets are getting organized. But to demagnetize it, it takes some time. Okay. So that's the same thing that is happening over here. So to demagnetize this core, you need an extra current, but that extra current is going in the opposite direction. It's going in the opposite direction. That is this direction, going in the negative direction. And at some point, whilst the current is going in the negative direction, then all these tiny magnets become as they were before when we started off at this point. Okay. So from here, you've come this much. You've used an extra amount of current, this much of extra current, okay, in order to make all those tiny magnets back into the hera-fairy position. Okay. This particular area where the magnets are not completely changed over into the hera-fairy position is called the area of retentivity. Okay, area of retentivity in one direction. And the current that is used, in other words, energy that is used to bring it back into the hera-fairy position is called the reverse current, and basically it is a wasted current. It is only doing this. It is not doing any useful force and useful work. Okay, and therefore this is wasted energy. When you're wasting energy, you are having a loss. So this is in one direction. Now we have gone, okay, following this, and then once again you reach a point of saturation in the opposite direction. Okay, where your current is at its maximum. Then again, your cycle is changing. You're coming again towards zero. So you will be following this particular curve, where just like in the positive side, on your negative side, the same thing is going to happen. Okay. When you have reached this point of saturation, instead of having north and south in this direction, you will have south and north in the opposite direction. So this time will be north and this time will be south. Okay. At this particular position over here. Then as the cycle is coming towards zero, again they will start becoming hera-fairy, but then still some magnets will be arranged in this manner. Exactly as we had in the positive half, we are having in the negative half. And as we said, we have to then increase the current in the opposite direction. So now we are coming this side. And at this particular point, that is this particular point, all the magnets have become hera-fairy. You are demagnetized the core. Once again, this particular area in the opposite direction is once again called the area of retentivity. And this double arrow over here showing the current, the magnetizing current, that is required extra for demagnetizing the core. Okay, so this entire curve is called the hysteresis curve, and the area in between is representative of the loss. And that is what is called as the hysteresis loss. Okay, so ideally you want this particular curve, okay, this particular diagram to have as slim a possible area. So the fatter this area, more the losses, less the area that is covered by this hysteresis curve, then your hysteresis loss is less. Okay, so basically you cannot really speaking reduce the losses unless you use certain material. If you're going to have a perfect conductor, perfect, okay, a perfect conductor and a perfect particular iron core, then your particular thing, if this was your hysteresis loss, you will be having just a line going right through and through. You will not be having this curve. Unfortunately, we do not have such a material that is perfect. So for whatever the materials you use, you can only reduce this curve. And by reducing the curve, you are going to be reducing this hysteresis loss. Everybody's clear? What is hysteresis loss? Any queries or doubts? Okay, so let us see a video on what is hysteresis loss. The video is in Hindi. Those who do not understand Hindi, if they followed my explanation, you will be able to follow the video without any trouble. Okay.
हिस्टेरेसिस लॉस क्या होता है? हम यह तो जानते हैं जब चार्ज मोशन में होता है तब मैग्नेटिक फील्ड बनाता है। न्यूक्लियस की परिक्रमा करता हुआ इलेक्ट्रॉन इस प्रकार मैग्नेटिक फील्ड बनाता है कि एक तरफ मैग्नेटिक लाइंस का उत्सर्जन होता है यानी नॉर्थ पोल बनता है और दूसरी तरफ मैग्नेटिक लाइन फोर्स का आगमन होता है यानी साउथ पोल बनता है। इस प्रकार एटम अपने आप में एक मैग्नेटिक डायपोल होता है।
एटम्स का झुंड मिलकर डोमेन्स बनाते हैं। जरूरी तो नहीं कि डोमेन्स में हर एटम का मैग्नेटिक अलाइनमेंट सेम हो। कुल मिलाकर डोमेन की बाहरी परिधि पर कुछ न कुछ रिजल्टेंट मैग्नेटिज्म मिलता है, यानी डोमेन भी अपने आप में एक मैग्नेटिक डायपोल होता है।
कुल मिलाकर कोई भी फेरोमैग्नेटिक मटेरियल जैसे लोहा, सिलिकॉन, स्टील आदि को मैग्नेटिक फील्ड में रखा जाता है तो मटेरियल में उपस्थित यह डायपोल मैग्नेटिक फील्ड के अनुसार अलाइंड होने लगते हैं। एक्सटर्नल फील्ड के नॉर्थ पोल की तरफ डायपोल का साउथ पोल अट्रैक्ट होता है और साउथ पोल की तरफ नॉर्थ। इस प्रकार एक्सटर्नल मैग्नेटिक फील्ड को एक आधार मिलता है, सपोर्ट मिलता है कि वह मटेरियल में से पास हो सके मजबूती के साथ। इसी कारण से फेरोमैग्नेटिक मटेरियल की परमिएबिलिटी यानी परागम्यता अधिक होती है और मैग्नेटिक फील्ड दूसरे माध्यम जैसे एयर की वजह फेरोमैग्नेटिक मटेरियल से गुजरना पसंद करती है। यही कारण है कि बहुत सारे इलेक्ट्रिकल मशीन्स जैसे मोटर, ट्रांसफार्मर आदि में कोर के रूप में फेरोमैग्नेटिक मटेरियल का उपयोग करा जाता है। मैग्नेटिक फील्ड को हटाने पर डायपोल्स फिर से इधर-उधर अलाइंड हो जाते हैं और मटेरियल के अंदर उत्पन्न हुआ मैग्नेटिज्म समाप्त हो जाता है। जैसे कि एक इलेक्ट्रिकल ट्रांसफार्मर में मैग्नेटिक फील्ड अल्टरनेटिंग नेचर की होती है, जिससे कोर के अंदर डायपोल अलाइनमेंट चलता रहता है। अलाइनमेंट के दौरान डायपोल्स की बाउंड्री आपस में रगड़ती है, फ्रिक्शन उत्पन्न होता है और हीट उत्पन्न होती है जो किसी काम की नहीं होती। इसे ही हिस्टेरेसिस लॉस कहते हैं।
हिस्टेरेसिस लॉस को हम BH कर्व के हेल्प से भी समझ सकते हैं। जैसे कि हमारे पास एक फेरोमैग्नेटिक मटेरियल है, जैसे ट्रांसफार्मर की कोर में यूज करते हैं सिलिकॉन स्टील। इसमें सारे डायपोल्स का अलाइनमेंट इधर उधर होता है और इन डायपोल्स का अलाइनमेंट ऐसा होता है कि ये एक दूसरे के मैग्नेटिज्म को कैंसिल आउट कर देते हैं। अब हम एक कर्व ड्रॉ करते हैं जिसे BH कर्व कहते हैं। यह ड्रॉ होता है H, यहाँ पर H एक्सटर्नल मैग्नेटिक फील्ड इंटेंसिटी है और B के बीच में। यहाँ पर B क्या है? B है मैग्नेटिक फ्लक्स डेंसिटी इनसाइड द मटेरियल। तो शुरुआत में जब कोई भी फील्ड, आप यहाँ देख सकते हैं कोई भी फील्ड नहीं है, कोई भी एक्सटर्नल फील्ड अप्लाई नहीं करी गई है, मटेरियल के अंदर मैग्नेटिक फ्लक्स डेंसिटी भी 0 होगी क्योंकि सारे डायपोल्स इधर उधर अलाइंड हैं और एक दूसरे के मैग्नेटिज्म को कैंसिल कर देंगे। फिर जब हम इस मटेरियल को किसी एक्सटर्नल मैग्नेटिक फील्ड में रखते हैं तब क्या होगा? आप देख सकते हैं कुछ डायपोल्स इस मैग्नेटिक फील्ड के अलोंग अलाइंड हो चुके हैं और यह मटेरियल क्या हो गया? मैग्नेटाइज हो गया। इसी प्रकार से हम देख सकते हैं कि जब हम मैग्नेटिक फील्ड इंटेंसिटी, एक्सटर्नल मैग्नेटिक फील्ड इंटेंसिटी को काफ़ी ज़्यादा बढ़ा देते हैं तो मटेरियल के अंदर मैग्नेटिक फ्लक्स डेंसिटी भी मैक्सिमम हो जाती है। लगभग सारे डायपोल्स अलाइंड हो जाते हैं और फिर इसके बाद यह मटेरियल फर्दर मैग्नेटाइज नहीं होगा। इस वजह से आप देख सकते हैं यह कर्व धीरे धीरे जाके यहाँ पर फ्लैट हो जाता है। इसके बाद हम कितनी भी मैग्नेटिक फील्ड इंटेंसिटी को बढ़ाते जाएं एक्सटर्नली, मटेरियल के अंदर मैग्नेटिक फ्लक्स डेंसिटी कांस्टेंट हो जाएगी और इस कंडीशन को कहते हैं कंडीशन ऑफ सैचुरेशन। यहाँ पर मटेरियल में सैचुरेशन आ गया, इससे ज़्यादा यह मैग्नेटाइज नहीं हो सकता। इसी प्रकार अब हम एक्सटर्नल फ्लक्स को कम करेंगे तो वापस से ये जो डायपोल्स हैं इधर उधर अलाइंड होंगे और अगर हम एक्सटर्नल मैग्नेटिक फील्ड को कम कर 0 कर दें तब हम देखेंगे कि यहाँ पर मटेरियल में थोड़ा सा मैग्नेटिज्म रह जाता है। मटेरियल के अंदर थोड़ी सी फ्लक्स डेंसिटी रहती है, थोड़ा सा मैग्नेटिज्म रह जाता है। इसे बोलते हैं रेसिडुअल मैग्नेटिज्म, जो कि यहाँ पर रिप्रेजेंट हो रहा है BR से। यह इसलिए है क्योंकि सारे डायपोल्स वापस से अपनी इनिशियल पोजीशन में अलाइन नहीं हो पाए। आप देख सकते हैं यह डायपोल, यह डायपोल, यह डायपोल अभी भी एक ही डायरेक्शन में अलाइंड है, जिसकी वजह से मटेरियल के अंदर थोड़ा सा मैग्नेटिज्म बच जाता है। अब इन डायपोल्स को वापस से अपनी इनिशियल पोजीशन में लाने के लिए हमें मटेरियल को विपरीत दिशा में मैग्नेटाइज करना होता है। उसके लिए हम एक्सटर्नल मैग्नेटिक फील्ड को रिवर्स डायरेक्शन में अप्लाई करेंगे। यहाँ से लेकर जैसे जैसे हम रिवर्स डायरेक्शन में मैग्नेटिक फील्ड को बढ़ाएंगे, धीरे धीरे ये डायपोल्स वापस से अपनी इनिशियल पोजीशन में आएंगे और इधर आने पर आप देख सकते हैं मटेरियल के अंदर जो फ्लक्स डेंसिटी है वो 0 हो जाएगी। उसके लिए हमें कितना एक्सटर्नल मैग्नेटिक फील्ड लगानी पड़ेगी? वो लगभग उसकी स्ट्रेंथ होगी इतनी। इसे बोलते हैं कोहेसिव फोर्स। कोहेसिव फोर्स वह फोर्स है, वह मैग्नेटिक फील्ड है जिसे विपरीत दिशा में अप्लाई करना होता है रेसिडुअल मैग्नेटिज्म को खत्म करने के लिए। इसी प्रकार में हम नेगेटिव डायरेक्शन में, ये देख सकते हैं हमने नेगेटिव डायरेक्शन में मैग्नेटिक फील्ड लगाई हुई है और हम और भी ज्यादा मैग्नेटिक फील्ड को नेगेटिव डायरेक्शन में बढ़ाएंगे तो फिर यह डायपोल्स विपरीत दिशा में अलाइंड होना शुरू हो जाएंगे। अब आप देख सकते हैं काफी सारे डायपोल्स नेगेटिव डायरेक्शन में अलाइंड हो चुके हैं, लेकिन अभी भी पूरे डायपोल्स अलाइंड हुए नहीं है। तो यहाँ से यहाँ तक तो ग्राफ हमें लगभग थोड़ा सा लीनियर मिलेगा। उसके बाद जैसे जैसे सैचुरेशन आना स्टार्ट होगा यह ग्राफ हमारा ऑलमोस्ट कांस्टेंट हो जाएगा। जैसे हमने एक लिमिट से ज्यादा मैग्नेटिक फील्ड, एक्सटर्नल मैग्नेटिक फील्ड को बढ़ाएंगे, उसके बाद हमारा मटेरियल फर्दर मैग्नेटाइज नहीं होगा क्योंकि सारे ही डायपोल अलाइंड हो चुके होंगे। अगेन दूसरी दिशा में नेगेटिव डायरेक्शन में भी आपका सैचुरेशन आ जाएगा। वही प्रोसेस अगेन रिपीट होगी। हम एक्सटर्नल मैग्नेटिक फील्ड को कम करेंगे तो यह डायपोल्स वापस से इनिशियल पोजीशन में आने की कोशिश करेंगे। यहाँ आप देख सकते हैं हमने एक्सटर्नल मैग्नेटिक फील्ड को वापस से रिड्यूस करा और हमारे मटेरियल के अंदर मैग्नेटिज्म की फ्लक्स डेंसिटी की वैल्यू इतनी होगी। और इस बार भी वही होगा, हम जब एक्सटर्नल मैग्नेटिक फील्ड को पूरी तरीके से हटा देंगे उसके बाद भी हमारे जो
डायपोल्स हैं वो कुछ डायपोल्स अलाइंड रह जाएंगे, अगेन मटेरियल के अंदर रेसिडुअल मैग्नेटिज्म बच जाएगा और इस रेसिडुअल मैग्नेटिज्म को खत्म करने के लिए हमें इस बार से विपरीत दिशा में, यानी हमें मटेरियल को वापस से एक्सटर्नल मैग्नेटिक फील्ड की हेल्प से हमें मैग्नेटाइज करना होगा। तो हम देख सकते हैं यहाँ पर हम इतनी पॉजिटिव फील्ड हमें अगेन लगानी पड़ेगी ताकि हमारा मटेरियल के जो डायपोल्स हैं वो पूरी तरीके से इधर उधर अलाइंड हो जाए और हमारे मटेरियल का रेसिडुअल मैग्नेटिज्म खत्म हो जाए। तो इस प्रकार से यह कर्व ऐसे फॉलो होता रहेगा। हम पॉजिटिव डायरेक्शन में फील्ड को लगाएंगे, हमारा मटेरियल मैग्नेटाइज होगा, सैचुरेशन आएगा, फिर एक्सटर्नल फील्ड को हटाने पर मटेरियल के अंदर मैग्नेटिज्म रह जाएगा। उस मैग्नेटिज्म को खत्म करने के लिए हमें विपरीत दिशा में मैग्नेटाइज करना होगा, फिर जाके हमारे मटेरियल के अंदर फ्लक्स डेंसिटी 0 होगी। फिर अगेन हमें नेगेटिव डायरेक्शन में और ज़्यादा हम मैग्नेटाइज करेंगे एक्सटर्नल फील्ड की हेल्प से, तो अगेन सैचुरेशन आएगा और ये कर्व फॉलो होता रहेगा। हमारे मटेरियल हर मटेरियल के लिए हिस्टेरेसिस कर्व डिफाइन होता है। जिन मटेरियल के हिस्टेरेसिस कर्व के अंदर ज़्यादा एरिया होता है उनमें हिस्टेरेसिस लॉस ज़्यादा होता है, और एक आइडियल फेरोमैग्नेटिक मटेरियल क्या होगा, उसके अंदर इस कर्व के अंदर का जो एरिया है वो 0 होगा। मतलब यहाँ से यहाँ तक एक स्ट्रेट लाइन होगी। मतलब जैसे जैसे एक्सटर्नल मैग्नेटिक फील्ड को बढ़ाएंगे मटेरियल के अंदर फ्लक्स डेंसिटी लीनियरली बढ़ेगी और फिर एक्सटर्नल मैग्नेटिक फील्ड को 0 करने पे फ्लक्स डेंसिटी भी 0 हो जाएगी। इसका मतलब आइडियल फेरोमैग्नेटिक मटेरियल का जो हिस्टेरेसिस कर्व होगा वो कुछ इस प्रकार होगा, एकदम स्ट्रेट लाइन, और उसके अंदर जो एरिया होगा वो 0 होगा, यानी उसके अंदर कोई हिस्टेरेसिस लॉस नहीं होगा। लेकिन यह पॉसिबल नहीं है,
फ्रिक्शन तो होगा, इस प्रकार BH कर्व भी बनेगा। तो यह होता है हिस्टेरेसिस लॉस। तो आशा करते हैं कि अब आप समझ चुके होंगे कि हिस्टेरेसिस लॉस क्या होता है और आपको यह वीडियो पसंद आया होगा। अगर हाँ तो इस वीडियो को लाइक और शेयर ज़रूर करें। दोस्तों, अगर आपने हमारे
Okay, so having heard my explanation and seen the video, I hope you understand now what is hysteresis loss. You can only reduce this hysteresis loss by reducing this curve, and by reducing the curve, you have to try and get a particular material that will not take so long to get back into the hera-fairy position. Okay. As he said, if you have a very ideal core, then the line would be straight. But unfortunately, that is not possible at all. Okay. Okay. So auto transformers will put very little effort into this because we have already seen how an auto transformer works. Most transformers have two separate windings, primary winding and secondary winding. Therefore, when you are going to be using more copper, the cost is going to increase. Not only does the cost increase, your I²R losses increase or copper losses increase. Okay, so if you're going to have an auto transformer, and we saw what is an auto transformer, is having only one winding. And then you're going to have your secondary as a tapping from that. Okay, so correspondingly, your auto transformer is going to cost less because we are using less copper. Also, your I²R losses are less because of the copper that is going to be used is less. Okay, and therefore your efficiency of your auto transformer is much higher than your normal transformer. Okay, and as we saw, where they are going to be used, we are going to be using the same thing in your motor starters, and we already discussed that when we did the motor starters using an auto transformer. Okay, everybody clear? Any queries or doubts on your transformers? With this, we complete the entire cycle of all the topics that I take. Any queries or doubt on this particular topic? Okay, so with that, let us move on to a new topic. When I say a new topic means we have already, those who have been old students would have already done this topic with me. And then we progress and come back to transformers sometime, either end of next month or early March. Okay. So generally 1 month, 10 days, 1 month, 15 days, depending on how many holidays we have in between. And sometimes I do need to take an off in between for some reasons. So a few days this side or that side, or 1 month, 10 days. Okay. Right. So sensors. Question is asked is, what is a sensor? Okay. They are devices that are used to detect and respond to electrical or other signals, converting a physical parameter into an electrical signal that can be measured and displayed at a remote position. So over here, you can add that particular thing, displayed at a remote position. Okay. So what are those parameters that can be measured? A physical parameter, as you can see, temperature, pressure, speed, flow, all those things are physical parameters. A sensor is going to detect that, convert it into an electrical signal. Of course, it is measured electrically. And then at a remote position, you can see what that is. Just like you don't have to go down to see your exhaust gas temperatures of your main engine. You can read it right there on those screens. Okay, when we did the AMS system, we have 2 screens, isn't it? So we can read it on those screens. We open that particular page and we can see the particular parameter that we are talking about. And in this case, the exhaust gas temperature of your particular main engine, okay, or that particular main engine unit. Now, your sensors are of 2 types, active type and passive type. The active sensor is that sensor that is capable of producing its own voltage and working off that particular voltage. It does not require 24 volts DC or 5 volts DC or whatever it is. It does not require any external source for it to work. Such a sensor is called an active sensor, and a good example of that sensor is your thermocouple, which we will be discussing when we are doing temperature sensors. What about passive sensor? Obviously, it is the opposite of an active sensor, where your passive sensor requires an external power source. For example, 20 or 30 volts DC, it requires that. And only then will it work. If you don't give that external power supply voltage, it is not going to work. And a very good example is just like that exhaust gas temperature sensor that I mentioned. That is an RTD, or resistance temperature detector, which again we'll be discussing when we are going to be doing the temperature sensors. Okay, so active sensor, passive sensor. Now, sensors that we are going to discuss are generally sensors on board the ship. What are they? What are being used on board ship? Okay, we are not going to go into sensors that are used ashore. Yes, generally even ashore, most of the same sensors are used. But there are certain sensors that are used ashore and definitely not on board ship. Okay, so the types of sensors that we will be discussing: pressure sensor, temperature sensor, flow sensor, level sensors, proximity sensors, and then your fire detection sensors of smoke, heat, and flame. At this particular juncture, I would like to inform you that some of these sensors are not practical for use on board ship and will not generally be used on board ship. Okay, mark my words. Some sensors are not practical for use on board ship. Okay, and generally you will not find those type of sensors on board the ship. But we must know the principle of operation And therefore, when you are questioned in the examination, you have to know how that particular sensor would work. The main thing is principle of operation. Okay, so let's take the very first one over here, the pressure sensors. Okay, pressure sensors. Again, a question that can be asked is, what is a pressure sensor? It's a device that generates a signal as a function of pressure or force. So that pressure is a physical parameter. Remember the definition of your sensor. Okay, which is then going to be changed into an electrical signal. So pressure or force, that gives us a reading of that pressure or force being imposed electrically at a remote position. Okay, so it is going to give us a reading. Okay, it can give you a local reading. It can give you at a remote position. And if it is going to be at a remote position, then it will be changed into an electrical signal. And that electrical signal is going to give us that same reading from that pressure sensor, okay, at a remote position, okay. Used for measuring gases, liquids, okay. They can also be used indirectly for flow, and we'll be seeing that when we are doing the flow sensors. It can be used for level, it can be used for altitude. Okay, if somebody remembers, there was a Air France flight that took off, this was some years back, that took off from Brasilia, which is the capital of Brazil. Okay, and it was on the way to Charles de Gaulle airport in Paris, and somewhere near Morocco or somewhere over there, but it was mid-Atlantic. Okay, suddenly that plane disappeared. It just dived into the sea. Okay, later on when they recovered, they managed to recover the black box. They found, and if you ever notice when you are boarding the aircraft to join your ship, generally you board from the front side, right? Right by where the pilots and all are sitting. Just notice next time when you are getting over there, just notice, just below the pilot's window, there is a structure that is looking something like this. So, okay, let me make this like the pilot's window over here. There is a structure that is pointing this way. Okay, like that. Not only on the main pilot side, on the co-pilot side, on the other side, that is on the starboard side. Pilot sits on the port side. Okay, so there is a small thing like this, which is pointing forward. Likewise on the starboard side. Now what had happened? This is a pressure sensor. So as you are going higher, your pressure gets lower. And as you're coming down, your pressure becomes higher. Okay, so now this one was showing something, and the one on the co-pilot side was showing something else. So the pilot was looking at his instrument, the instrument panel, and was doing the correction depending on the reading that he was getting from his particular pressure sensor with regard to the altitude. So what he was doing, I think he was getting less altitude, whereas, you know, you have to be at 35,000 or thereabouts, 35 to 38,000 feet. They normally cruise when you're going a long distance. Okay. So he was getting a wrong altitude where the traffic controller had said you have to be at so-and-so height. Okay, as they're passing along there, maybe the Morocco ATC said you are good to go, but he was looking at, instead of, say he was supposed to be at 38 and he was getting 35,000. So what did he do? He had to correct that thing because he was reading it from this pressure sensor. So he started to put the nose up, and the aircraft started going up. Okay, whereas your starboard sensor was giving the correct altitude, it was giving this. So the pilots was giving this, the co-pilots was giving this. And the co-pilot didn't even notice. Okay, so this guy started putting the nose up. The plane was put up like that, started to climb. In other words, it went into a stall. And then once it goes into a stall, you cannot generally control the aircraft. It just nosedived into the ocean. So they found that this sensor, a pressure sensor, had malfunctioned. Okay, so as we said over here, it is used also for determining altitude. Okay, so once you know, or once the question is asked is what is a pressure sensor, then you give that answer and then he can ask you what is pressure. Okay, pressure, as we know, is force. Okay, so it is the force applied, everybody would say, to a surface per unit area. Okay, and we leave it at that. Now, as I said, you always should look at the examiner's face. Normally, they don't have poker faces. Poker faces means they don't give any idea with regard to whether you've answered correctly or not. They generally have some expression on their face. Sometimes they nod, sometimes they shake their head, sometimes they, they give a quizzical look. Okay, all those are signs that you have or may have answered wrongly. So when you're giving the answer, do look at the examiner's face, and that will tell you whether your answer is correct or not. So whilst most of us will say force applied on an object per unit area, yes, we are correct. But we have to be very correct because we are using this pressure to be transmitted by a sensor to a remote position. So that force that is being applied on that surface object should be at a perpendicular angle. That means at 90 degrees. And as you can see here, this is 90 degrees. It is not acting in this direction. It is not acting in this direction. But if the force or the pressure is acting on the surface of an object at 90 degrees, if you cannot remember the word perpendicular, at 90 degrees, then that is called as pressure. So once again, defined as the force applied perpendicular or at right angles to a surface of an object per unit area. Okay, so that is what is pressure. Okay. Okay, so we've seen what is a pressure sensor, what is the definition of a pressure. So let us see over here, and we'll take it one by one. What are the type of pressure sensors that are available? So right at the beginning, I said certain pressure sensors are not practical for use on board ship, and one of those is your piezoelectric type of pressure sensor. You have capacitive, you have the electromagnetic, and you have the strain gauge. Piezoelectric type of pressure sensor is generally not used on board ship. We will come to when we do piezoelectric pressure sensor, we will see the reason why it is not found on board ship. Let's do the first one, the capacitive type of pressure sensor. Okay, so we are very familiar with this formula. C is equal to epsilon multiplied by A divided by D. Epsilon is the dielectric strength. Okay. Depending on what is the dielectric, each dielectric will have a different strength, epsilon. A is area of plates. Okay, generally a capacitor, the symbol is this. So the area of these two plates. D is the distance between the plates. Okay, so the area of the plates, if they change, your capacitance will change. If the distance between the two plates changes, your capacitance can change. Depending on the dielectric used in between those plates, the capacitance can change. Okay, so any of these three parameters, if it is going to change, your capacitance is going to change. This capacitance is then taken to an electronic circuit that converts capacitance into a level. Inches, feet, meters. Okay, that particular circuit is going to change the change of capacitance into a level. Okay, so now let's see, using a basic capacitive type of pressure sensor, let's see how that thing is going to come into play. Okay, so here's a very basic pressure sensor. One plate is a fixed plate over here, and you have the connection going to that electronic circuit that I spoke about. Here's another plate, but this plate is a diaphragm. A diaphragm, a metal diaphragm that too, that is flexible. Okay, so whenever force is acting at 90 degrees to this surface area, this diaphragm is obviously going to get deformed. So it will be depressed inwards. Okay, and from this particular flexible diaphragm, you are having another connection going to the electronic circuit that is going to be changing capacitance into a level. Now you can see that before force is enacted, okay, before force is enacted, that flexible diaphragm is in this position shown by a solid red color. Whatever force that is acting now on this flexible diaphragm has depressed it inwards and is shown now with a shaded red portion. Okay. Notice what is happening. Once again, C is equal to epsilon multiplied by A divided by D. Let's take the epsilon or the dielectric as air. Okay, so air, as you know, is 1. Okay, epsilon is 1. The dielectric strength of air is 1. Anything other than air is something greater than 1. So depending on what is the material that is being used over here, it can be either air, 1, something else, maybe 2, yet another material is 3, and so on and so forth. Okay, so we are just taking the simple one, air as 1. Okay, that's fine. Area of the plates is remaining same. It's not changing. What is changing is nothing but the distance. Initially, the distance is shown by the green double arrow. And now, because of the force that is acting on this particular flexible plate and pushed it inwards, that distance from the green has become this black double arrow. So notice the difference. The distance has changed from something of this distance. It has become to this distance. In other words, distance has decreased. When distance has decreased, obviously the capacitance is going to increase. And remember, the capacitance is then through these connections taken to an electrical circuit that is going to convert this change in capacitance into a pressure. And that pressure reading will be calibrated either in inches, feet, meters, okay, accordingly, and displayed. Okay, everybody is clear with regard to the basic pressure sensor and how it works? Right, let us see the other one, the strain gauge type of pressure sensor. Okay, before the strain gauge, let's go to the differential pressure sensor. Let me open up that particular thing. Right, okay, so we are still on pressure sensors. We'll do the strain gauge shortly. Okay, so we would have seen a differential pressure sensor looking something like this, especially for your boiler. Okay, so what is a differential pressure sensor? It has a diaphragm, and that diaphragm in between, where is that diaphragm located? If we're going to cut it in such a way, this is that diaphragm which is over here. So that is going to be a flexible diaphragm, and you're going to have that diaphragm which is going to be separating two capacitors, one capacitor on your left-hand side and one capacitor on your right-hand side. One wall of this capacitor is fixed, and the diaphragm is making or completing that particular capacitor. On the right-hand side, the fixed wall is forming the other plate of that capacitor, of another capacitor, and your diaphragm, which is being common for the capacitor on your left-hand side, is also acting as the second plate for the capacitor on the right-hand side. And of course, you're going to have connections not only from both the fixed plates, you will be also having one from the middle plate. Okay, look at this particular thing. Okay, this is a more clearer diagram. So you have two stationary plates with a diaphragm in between, and therefore you're having this one as one capacitor and this one as another capacitor. Outputs are taken, and therefore whatever is the capacitance difference, you're going to get that as the particular thing. So there is going to be a difference in this capacitance and this capacitance depending on what is the pressure that is going to be acting. Okay, so an electrical signal is then directly proportional to the difference in the two pressures. Okay, so that is a differential pressure transmitter. Once again, we are using the same formula. Now that same formula is going to be applied now for two capacitors. Okay, so once if this pressure is higher, then obviously this diaphragm is going to be deflecting towards the right-hand side. Okay, and if your pressure from this side, okay, we're always having high pressure, low pressure, this thing as far as your boiler is concerned. Low pressure is from your water drum, your high pressure is from your steam drum. Okay, and that is why we get the level of the water in the boiler using that principle. Okay, so either the high pressure side, the steam pressure can be higher, or your water pressure can be higher. If the water pressure is higher, then this particular diaphragm will bend towards the left-hand side. Okay, so let's see how that is going to happen over here. Right? If your high and low pressure areas, that means your steam drum pressure and your water pressure, both are equal, then that flexible diaphragm in the middle is not going to change its position. Okay, so the difference output, the voltage output from your left side particular, from your left side capacitor and the thing on your right-hand side of the capacitor, that is going to be zero. Okay, the capacitance is going to be zero. So that differential is then going to be sent to a differential amplifier, which is going to give you a 0 volt output. So now if your steam drum pressure is high as compared to your water drum, then of course your diaphragm is deflected towards the right-hand side. So your capacitance of this side capacitor is going to change. Oh, sorry. Yeah, it is going to change. Why? Is because this distance has now increased. When the distance is increased, the capacitance is going to decrease. From that formula, C is equal to epsilon multiplied by A divided by D. But the capacitance on your right-hand side has increased is because your distance between the two plates has decreased. So that differential of your capacitance is then sent to a differential amplifier, and then you will get a positive output. On the contrary, if your water drum pressure is higher than your steam drum pressure, then that flexible diaphragm, which is a common plate for both the capacitors, is going to be deflected towards the left-hand side. And this time, this distance has become more, which means the capacitance on the right-hand side capacitor has decreased. Whereas the distance between the fixed plate and the flexible plate on your left-hand side capacitor has decreased. Therefore, the capacitance is going to increase. And so for that differential that is there, that differential is sent to this particular amplifier, differential amplifier, and that will give you a negative voltage out. Okay. So whatever this positive and negative voltage output, that is going to be calibrated to give you that particular pressure that is being enacted on that particular diaphragm. Okay. Everybody clear with the differential pressure type of sensor? Any queries or doubts? Okay, so let us now see what is that strain gauge type. Then we'll come to the piezoelectric type. Okay, now this type of strain gauge pressure sensor is also called as the hull stress monitoring system, or it is used in the hull stress monitoring system. Okay, anybody has sailed on large size bulk carriers, Cape size bulk carriers greater than 100,000 ton dead weight? If anyone is going to sail sometime, I'm not sure whether it has become mandatory, but in those days when I was sailing on P&O bulk carriers, they had already installed these things on board. They had already installed the VER. Both these were not compulsory in those days when I was sailing with that company. Okay, so P&O was a very safety conscious company, and they used to go overboard with regards to safety. Okay, remember when we did the portable gas detection equipment, I said sometimes you may have 1 or 2 extra. These people used to have 5 or 6 extra. And I used to do the calibration. So it used to be a big headache. Every month I had to do the calibration of all those portable gas detection. They had quite a number of equipment. Okay. So coming to this, they had installed what was called the hull stress monitoring system. The hull stress monitoring system is using this type of pressure gauge, the strain gauge. Now, what is this? Just to give you a background before we go into the working, on the forward deck of the ship, forward of the accommodation, both on your starboard and your port side, you had boxes like this, okay? They were waterproof boxes. Inside that box, you had a solid stainless steel rod. The forward end was connected to the deck of your ship, and the other one was connected to what was called as the strain gauge in a Wheatstone bridge formation. Okay, so this was the strain gauge, and it was connected in a Wheatstone bridge configuration. Okay, so what is going to happen is, as you know, during heavy weather especially, your ship hogs and sags. Okay, this is hogging, this is sagging, and this is hogging. Sagging means your accommodation and your forecastle side go up and the midship goes downwards. Okay, this is exaggerated. It doesn't bend so much, but yes, it does bend. And the opposite, hogging, is when your accommodation and your forecastle side go down and the midship goes in the upward direction. So especially if you're on a tanker or even bulk carrier, you have pipes running, no, right from forward to aft. Those pipes are sort of telescopic pipes. And if you're seeing rough weather, then you see those pipes moving in and out of each other. Okay. If there were solid pipes going right through and through, and if the ship went through rough weather, then those pipes would rupture. Okay. So they are also going to be like telescopic pipes with one moving into the other to allow for this bending movement of the ship. Now, the bending movement of the ship, hogging and sagging, is detected by this particular thing. Although this is a solid stainless steel rod, this solid stainless steel rod bends in sympathy with the ship. And through that particular Wheatstone bridge having this strain gauge, the signal is transmitted to the bridge. The main unit is on the bridge. And then you are having a screen where it is going to be showing you what is the strain that your hull is going through at this position, all the sensors that are there. So if you are going to have these boxes like this on your port side, then in the in-between position of these two, you're going to have the corresponding one on your starboard side. And then you're going to have the bow one. Okay, because your bow bends very, very rapidly. Okay, if you're standing on any big ship, if you're standing on the bridge and you're going through rough weather, you will find the forecastle forward mast going up and down like this. That is why you have that rocking motion also whenever you're going through rough weather. Okay, that is the ship that is bending because of that particular thing. Okay. Now, how does this thing work? How does this strain gauge work? We said it is using the Wheatstone configuration, Wheatstone bridge configuration. And everybody knows that you're going to have 4 resistors. All the 4 resistors, if they are equal in every respect and you put a power supply to that Wheatstone bridge, then you are not going to get any current flow over here. So if R1, R2, R3, R4 are equal in every respect, then when the supply is given over here, you're not going to get any current flowing through the middle arm. Now, in the case of your Wheatstone, in the case of your hull stress monitoring system and the strain gauge is taking place of R4. So your R4 is nothing but the strain gauge over here. Okay. Now I'm going to demonstrate something for you. So I will activate my video. Give me a moment. Okay, so can everybody see me? And I'm holding in my hand a rubber band. Okay, can everybody see? Please answer.
Yes, sir.
Okay. Now only pay attention to the section on the top. Forget about the bottom. Okay. Look at the section on the top. Now I have not done anything to the rubber band. The rubber band is thick on the top. And now I'm going to pull the rubber band. What has happened on the top? The rubber band has become thinner. I release the rubber band, it is becoming thicker. And I pull the rubber band, it's becoming thinner on the top. Okay? Right. Now imagine that it was a wire. Okay? A wire that at one time is thick, and then a wire that is another time that has become thin. What is the cross-sectional area when it is like this? What is the cross-sectional area when it is like this? Is the cross-sectional area more this way, or is the cross-sectional more or less this way? I'm going to deactivate my video. So please answer that question. Anyone?
So the cross-sectional area will decrease when we will elongate the wire.
Okay. So when the ship is hogging or sagging, when it is hogging, okay, that means that particular rod, that stainless steel rod, is now bending this way. Okay. So that is what your rubber band is doing. So now I'm going to indicate that rubber band. At one time it was like that. Now the rubber band has become like this. That stainless steel rod is becoming or putting a pressure on this strain gauge. This strain gauge is a metal wire that is now becoming like this. So one time that strain gauge was like this. Another time the strain gauge is like this. So the cross-sectional area is become less over here. When the cross-sectional area is going to become less, what did we say? Rho is directly proportional to L over A. So if cross-sectional area is decreased, your resistivity is going to increase. In other words, R4 value is going to increase. When R4 value is increasing, now your Wheatstone bridge that was balanced has become imbalanced, and you will have a current flow going through the middle. Okay, so this is going to be calibrated and sent to that particular main unit on the bridge as to what is the pressure that is acting on this particular stainless steel rod. Okay, let me now redraw that in a box. Okay, so that stainless steel rod, now how much has it bent? How much of pressure is coming on this particular thing? That is now going to be calibrated with this amount of current, and that is going to be shown on the bridge. Okay, so much of extra stress is coming on my particular hull of the ship. So they will be having limits set. If the hull stress is going through too much of stress, you will be getting audible and visual alarms on that particular screen, and that will be an indication to the captain, hey, just slow down the ship, man. You're putting your ship's hull under too much of stress. Okay, because that if you're going to put that too much of stress, especially if you're carrying iron ore, then your particular ship is just going to break in two and sink. A case in example, there was a ship called Mineral Diamond. This was years and years ago when I was much younger and sailing at that time. We were sailing already from Australia to Rotterdam. We had loaded coal. And we were somewhere off South Africa when we got the news that Mineral Diamond had sunk. Okay, what had happened? She had loaded iron ore at the port of Dampier. They didn't, it belonged to a company called Bosimar, a Belgian company. They had loaded iron ore from the port of Dampier and set sail. Now, what that chief officer did, how they loaded the ship, but when they sailed, they went smack bang into a very severe cyclone. And when they went into that cyclone, obviously the hull went through too much of stress and strain, broke in two, and within 5 minutes, less than 5 minutes, okay, the ship sank with all people lost on board. Okay, they had already the VDR was already installed. So when they recovered that, they came to know, because the strain gauge input is also fed into the VDR. So they came to know that the strain gauge was giving a lot of alarms and that the master did not slow down the vessel adequately. Okay, you have to really slow down because you don't know. And your iron ore is a very heavy and a very stiff cargo. Your ship becomes like a dry twig, and when it bends too much, that twig is going to break, and that is exactly what happened in that particular case. So Mineral Diamond sank with all hands on board. Nobody was recovered. Okay? Right, so we will end our class over here. Tomorrow we will do, tomorrow is a holiday, 26th of January is a holiday, so not tomorrow, but on Friday, the 27th, we will be completing the pressure sensors and then moving on to the next set of sensors. Okay, I think we'll be starting on proximity sensors. So we will complete our pressure sensors and then move on to the proximity sensors. So everybody's understood all the pressure gauge, pressure sensors that we discussed so far. We need to do the piezoelectric pressure sensor and the electromagnetic pressure sensor. Before we end, let us see a video of this, okay, and how it actually works, and then we will close down our class. Okay. Okay, then. So we'll end today's class here today. And on Friday, we will continue with the sensor topic. Okay, we'll complete the pressure sensors. Okay, the piezoelectric type, the electromagnetic type, and then move on to the proximity sensors. Okay. So thank you very much for joining. Take care. Have a great 26th of January. And I will see you on the 27th at 11 o'clock.
Thank you, sir.
Welcome.